We will utilize this example to explain this update formula. The notation used here, S indicates the entering variable. R indicates the leaving variable index. We write in the very beginning for revised syntax method. So here, we write them. So it means that it goes to the R's row. The R's row actually choose the minimum ratio, and it is replaced by XS. And when we calculate the right-hand side value is actually the minimum ratio. We'll check that later. We will utilize the and the rest of them. The rest of the right-hand side is utilize the original right-hand side value minus theta multiplied by the constraint coefficient AI S bar. Okay, so actually it do a little bit like Gaussian interpolation. We utilize the example to check that. Suppose in the first iteration we have the V bar is 6. Remember that? In the first iteration, the V bar is okay, and the theta is the minimum ratio value is 8. That's the 0.25 and 0.25. Okay, so the theta is 8. Here S is 3. Right, and R is which row? R actually indicates which row? 2, right? And so second rows, so we want to find B2. The index for B2 is, that's why she says it's 5. Indicates the X5. Okay. Okay. I indicates which row. I equals 1 indicates the first row, second row, third row. Okay. So the I indicates the second row in the minimum ratio. Okay. But I want to know which specific variable leaves the basis. So we go back to the second row and try to find which variable leaves the basis. Okay. Okay. So based on this, we want to utilize this example and to introduce this idea. So we know the B2 new is we should B1 new, B2 new, I choose I start from B2 new because the B2 new is we already know. The B2 new is eight. Here B2 new, actually B2 is our R, right? It's the ratio, it's the minimum ratio. And we already know the minimum ratio is 8. Okay. So then we want to show how can we apply this formula. That will be B1 bar minus theta multiplied by A1 3. Right? So B1 bar is 16. Theta is 8. And the A1 3 bar is minus 1. So that is 24. So B3 bar ning is B3 bar minus theta is 3 bar. So that is 4 minus 8 multiplied by 0.25. That is 2. So the B new bar is 24, 8, 2. Right? That's the next iterations. Right hand side. Actually, as what I say, just keep the key point here is the minimum ratio. Minimum ratio, once we replace that, the minimum ratio is our right hand side value. And the next thing is to Gaussian elimination. Actually, this is the Gaussian elimination. Okay. If you want to do, you can do that by yourself. You transform them to table form, and you will see this type of calculation in Gaussian elimination. Okay. This one is actually the Gaussian elimination. You didn't figure it out because I utilize the matrix multiplication. In the matrix multiplication, you didn't see that. But if you transform them to table form, and you utilize table form to calculate again, you'll find this calculation. Okay, that's to update B bar. We don't have to calculate it again. We don't have to do that. We just update like this. Okay, that'll be easy, right? Next thing is we want to update AB inverse because we say it's not easy to find AB inverse. So again, we want to utilize the result of one iteration, and we update that to the next iteration. Okay. So in one iteration, we have AB inverse. Just in first iteration, we already find our AB inverse like this. And we have A dot in the iterations. X3 is the entering variable. Right? And our AB inverse like this. Okay? So the next thing is that we do the Gaussian elimination. If X3 is the backseat variable, in the following iteration, A.3 bar should look like 0, 0, 1, 0. Because the second row is replaced by X3. So that's a 1. And the rest of the column, the rest of the element should be 0. Okay? Okay. So what do we do here? How can we transform from here to here? The second row, multiply by 2. 0.5 multiplied by 2 becomes 1. Right? And how can I eliminate minus 1? Gaussian elimination, because right now this one is the bigger row. we want to eliminate the -1 and eliminate the -0.5. So how can I do? Multiply by 2 and add to the first row, right? Okay. And how can I do for the second, the third row? Right? Okay. Okay. So here we do remember that the Gaussian enumeration is the calculation actually is the entire row. Okay, so I just show you what happened in this column. So the rest of the column should do the same thing. So the second row I have to multiply by 2, right? So it becomes 0, 2, and -4. Okay? And then I say I want to multiply by the second row, multiply by 2 and add to the first row, right? So multiply by 2 and add to the first row, it becomes 1, 2, -8. Right? Second row multiply by 2 and add to the first row. And for the third row, the calculation is 1 multiplied by half. It should be -half, and then to the third row. Sure. So it becomes. Say that again? 0. -half. Are you sure? -2 multiplied by -0.5 is equals to 1. 1 and then 2. Check that. This one is the AB inverse nu. Is that correct? That's the first iteration, that's the second iteration. Okay, so the key actually, that's why I say in the table form we utilize Gaussian enumeration. So we can utilize the Gaussian enumeration to update the matrix. Okay. So the key point actually is here. Because we want to transform the basic variable to the stem. So the rest of the row will do the same calculation. Like that. Okay? So you can update. Yeah.
So by this way, we still have to create at least once A1 inverse, the AB inverse.
Should I? I already updated, right?
You need the
I need the first one. I need the first iterations. But do I have to do that?
Oh, this I didn't also.
I can go from the first initial one, right? Initial one identity matrix, but let's enter in basic variable, and I do the same Gaussian enumeration. I can update to AB inverse. Okay, we can try that for the other problems. We 开始不是就有 identity matrix 了吗？那假设我的忘了我的 x2 entering 对不对？那我就可以把 x2 不知道什么东西对不对？那我把它 update 变成001的样子。那我装着运算的时候，这个 identity matrix 是不是就会跟着变？对啊，就变成这个了，不是吗？那跟着这个之后，我现在 x3 entering 的时候，我是不是就 update 又变成这个？它其实是一直 update， 就变从原本的 identity matrix， 然后 update 变成这个。所以我不用算 AB inverse。In the initial step, actually it's identity matrix. In the first iteration, we have forgot which variable entering. Based on like entering variables, we can update to 001 or something. And once we update this identity matrix, we update to a new matrix like this. Okay? So the following step, so that's why I say I only tell you from one iteration to the next iteration. That's from the first iteration to the second iteration. The idea is the same, but just you can use a lot of Gaussian enumeration. Okay? So actually you don't have to, in this way you don't have to calculate AB inverse. Okay? So the z bar indicates, suppose this one, and the z bar indicates the value, the objective function of the new iteration. Okay, so again, we utilize the example we had previously. We utilize the same example. S is 3, and in the iteration, C is the objective function value is 240, right? So C is equals to C3 is -5. That's what we calculate because it's not optimum, so we go to the next iteration. Remember that? So based on this formula, is 240 minus the theta is 8. We already calculated. I CS bar is here. Minus 5. Okay. Okay. So if I utilize this observation 1, 2, 3, actually I already applied the table 4 because we utilize the Gaussian enumeration to do this kind of calculations. Okay. Go back to check that. What do we multiply by? -8 because we want to eliminate CS or C3 bar from -5 to 0. Remember that? Because the backseat value for that's the backseat value. The objective function coefficient should be 0. So the second row should multiply 5, adding to the objective function. Okay. So actually this observation is the combination of the revised simplex method and the temporal form. Okay, so as what I said, algebra form, table form, and reverse simplex method actually they are the same thing, but it must just utilize different form to do the calculation. Okay. Let's know which one is better than the other. No. We provide different methods. That's because in different scenarios, different situations, some method will be easier for us to do the to verify something. For example, previously we asked you, if I already provide you say basic variable is like this, and ask you this basic variable is optimum or not, we can utilize the revised simplex method to answer the question. Don't have to solve from the very beginning to the end. Okay. So that's why you learn a lot of technique. Okay. Any questions? Okay. So the following we're talking about another technique. Before we start, I forgot to give you homework. 'Your choice. The due date will be 3 weeks from now or 2 weeks from now. So that will be April
7.
7. Are you sure?
40.
3 weeks.
40.
Okay, so far we are talking about simple. When we try to solve an example, solve a problem, it's a simple problem. So always we can find that that's optimal, unbounded, or infeasible, right? So when talking about the termination of the simplex method, you find that. Why should I talk about that? Because always I know the results. But in the real world problem, that's a complex one. Sometimes it's not easy to find. Sometimes it's not easy to find optimal solution. Or maybe you routinely find the same problem or same solution. It wastes you a lot of time. before we're talking about the termination of simplex method, we talk about degenerate. We define a degenerate. Actually, we talk about when we talk about the dictionary, we already mentioned non-degenerate, right? No? Go back to your note. At that time, we talked about non-degenerate, but I didn't define it. I just tell you the scenario. And you already know degenerate, because you already know degenerate. And I want to mention it again because here we mentioned about the theta, the ratio test. If we find the theta, the ratio test is equals to 0. So it means that, remember that we debug new. If the theta is equals to 0, it means that some basic variable is equals to 0. Some basic variable equals to 0, we call it degenerate. Okay? And we don't like this. We prefer non-degenerate because non-degenerate will give me information about basic variable. Okay? The observation is that if the current basic feasible solution is non-degenerate, it means that right hand side greater than 0, then the current iteration is always non-degenerate. Okay? And how can I prove? If the basic variable is non-degenerate, what does that mean? The right hand side greater than 0. Okay? How can you guarantee the right hand side greater than 0? The next iteration. Always greater than 0. If our right hand side is always greater than 0, and we choose, when we do the ratio test, we only choose the constant coefficient greater than 0, right? So the ratio, the minimum ratio will be, is that possible equals to 0?
So yes.
Yes to what? Your B bar is always greater than 0, and you divide by greater than 0. So we're always greater than 0, right? So when we go to the next iteration, our right hand side, or our ratio test, the ratio, we can guarantee the ratio. Right now we only can guarantee the ratio, but the rest of them, we do the Gaussian elimination, we cannot guarantee that. But we can guarantee the ratio greater than 0. Okay? current iteration is always non-degenerate, means that when I enter in a new backseat variable, it's non-degenerate. So it always give me the ratio greater than 0. So non-degenerate means that in the next step, my z will improve because theta greater than 0, right? So the z value will increase, right? Right. Actually, this one related to the previous observation 1 to 3. When I update V bar, when I update AB versus the third one is update Z. Update Z, we need this set. Okay? So that's what we mentioned here. Okay? Why? So let's go back to the previous update formula. Why this one is so important? Because when we try to update the V bar, the right hand side, or the Z value, we need theta. Okay? Check the previous update formula. You will see that when we update the value, right hand side, the Z value, we need theta. So once the theta greater than 0, we have a new V bar Z and the increase Z value. Okay. Okay. Here, the Z value. Once the theta greater than 0, we have greater Z bar new. Okay. 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 Previous iota is a Z bar new and Z bar indicates the original one and the new one. But here iota is another notation. Okay. The iota is x tilde and the z tilde. Okay. For the part I already erased, actually the x tilde indicates the x bar new. Z tilde indicates the z bar new. Okay. It's the next iteration. It's the following iteration I have according to the current iterations information. Okay. So here I will utilize bar indicates the current iteration. The tilde indicates the next iteration. Okay. So you can see actually that's what we had previously. Previously, I write down Z here, I utilize a Z bar new. Okay, but here I utilize Z tilde. Okay, the rest of things. remains the same. So xb tilde I update for the basic, actually as a right hand side value by, remember that? Previously actually it's the, okay, and want to know the basic feasible solution, the value of basic feasible solution, I utilize xb to indicate. Okay. I should add here to indicate several basic values. Okay. The I will be first row, second row, so mth row. Exclude the last row because the last row give me theta is the theta, right? That's the minimum ratio. Because the last row I don't have to do this kind of calculation because they give me a theta. The x. The last row indicates the xs as the entering value, and the value of that is minimum ratio. Okay. So the basic variable, the value is basic variable. Why non-degenerate is so important? This is the update formula, right? So we can compare in the new iterations, tilde, and the original iterations, but if they different or not. So once the theta is greater than 0, in the next iteration, we have totally different right-hand side. It's impossible to have exactly the same basic feasible solution value. And also, that's most important, it should be greater than the new objective function value should be greater than the original one. Means I improve. After the simplex method, I will improve. If you do the simplex method and from one iteration to the next iteration, you find your z doesn't improve. And maybe decrease, you are in trouble, right? Okay. And we will continue next week, we'll talk about, because we talk about termination. So next week we'll talk about if it is impossible, x tilde equals to x bar, z tilde equals to z bar, and what can we do? That will be next week. Okay, any questions? See you next week.